3.4.1 Measurement of the conductivity of ionic solutions. We know that accurate measurement of an unknown resistance can be performed on a Wheatstone bridge. However, for measuring the resistance of an ionic solution, we face two problems. Firstly, passing direct current DC changes the composition of the solution. Secondly, a solution cannot be connected to the bridge like a metallic wire or other solid conductor. The first difficulty is resolved by using an alternating current, that is AC, source of power, and the second problem is solved by using a specially designed vessel called Conductivity Cell. It is available in several designs and two simple ones are shown in figure 3.4. Here you can see the two different types of conductivity cell. Basically, it consists of two platinum electrodes coated with platinum black, that is finally divided metallic platinum is deposited on the electrodes electrochemically. These have area of cross section equal to A and are separated by distance L. Therefore, solution confined between these electrodes is a column of length L and area of cross section A. The resistance of such a column of solution is given by the equation R is equals to rho L upon A is equals to L upon Ka or kappa A. The quantity L upon A is called cell constant, denoted by the symbol, and it depends on the distance between the electrodes and their area of cross section and has the dimension of the length, that is per length you can say, and can be calculated if we know L and A. Measurement of L and A is not only inconvenient but also unreliable. The cell constant is usually determined by measuring the resistance of the cell containing a solution whose conductivity is already known. For this purpose, we generally use KCl solution whose conductivity is known accurately at various concentration, and here is the table 3.3 for that, and at different temperature. The cell's constant Chi is then given by the equation is equals to L upon A or R kappa. Here you can see the conductivity and the molar conductivity of KCl solution at 298.15 K. Once the cell constant is determined, we can use it for measuring the resistance or conductivity of any solution. The setup for the measurement of the resistance is shown in figure 3.5. It consists of the two resistance R3 and R4. A variable resistance R1 and the conductivity cell having the unknown resistance, that is the R2. The Wheatstone bridge is fed by an oscillator O, that is a source of AC power in the audio frequency range between 550 to 5000 cycles per second. P is a suitable detector, and that is a headphone or other electronic device, and the bridge is balanced when no current passes through the detector under these conditions. Unknown resistance R2 is equals to R1 R4 upon R3. These days, expensive conductivity meters are available which can directly read the conductance or resistance of the solution in the conductivity cell. Once the cell constant and the resistance of the solution in the cell is determined, the conductivity of the solution is given by the equation kappa is equals to cell constant upon R, that is G upon R. The conductivity of solution of different electrolytes in the same solvent and at a given temperature differs due to charge and the size of the ions in which they dissociate, the concentration of ions or ease with which the ions move under a potential gradient. It therefore becomes necessary to define a physically more meaningful quantity called molar conductivity and denoted by the symbol lambda. It is related to the conductivity of the solution by the equation molar conductivity is equals to K upon C. In the above equation, K is expressed in SM minus 1 and the concentration C in mole M minus 3, that is mole per meter cube. Then the units of lambda are in S meter square per mole. It may be noted that 1 mole per meter cube is equals to 1000 liter per meter cube multiplied by molarity, and hence it is having this formula. If we use S per centimeter as the units for kappa and mole per centimeter cube the units for the concentration, then the units for lambda are S centimeter square per mole. It can be calculated by using this equation, and both type of units are used in literature and are related to each other by the equation, that is 1s meter square per mole is equals to 10 to the power 4s centimeter square per mole, or 1s centimeter square per mole is equals to 10 to the power minus 4s meter square per mole. 3.4.2 Variation of conductivity and molar conductivity with concentration. Both conductivity and molar conductivity change with the concentration of the electrolyte. Conductivity always decreases with decrease in concentration both. For weak and strong electrolyte, this can be explained by the fact that the number of ions per unit volume that carry the current in a solution decreases on dilution. The conductivity of a solution at any given concentration is the conductance of 1 unit volume of solution kept between two platinum electrodes with unit area of cross section and at a distance of unit length. This is clear from the equation that G is equals to kappa A upon L is equals to kappa, where both A and L are unity in their appropriate units, meter or centimeter. Molar conductivity of a solution at a given concentration is the conductance of the volume V of solution containing 1 mole of electrolyte kept between two electrodes with area of cross section A and distance of unit length. Therefore, lambda is equals to kappa A upon L is equals to kappa, since L is equals to 1 and A is equals to V, volume containing 1 mole of electrolyte. Lambda is equals to kappa V. Molar conductivity increases with decrease in concentration. This is because the total volume V of solution containing 1 mole of electrolyte also increases. It has been found that decrease in kappa on dilution of a solution is more than compensated by increase in its volume. Physically, it means that at a given concentration, lambda can be defined as the conductance of the electrolytic solution kept between the electrodes of a conductivity cell at unit distance but having area of cross section large enough to accommodate sufficient volume of solution that contains 1 mole of the electrolyte. When concentration approaches 0, the molar conductivity is known as limiting molar conductivity and is represented by the symbol lambda naught. The variation in lambda with concentration is different, that is in figure 3.6 for strong and weak electrolytes. Now come to the strong electrolytes. For strong electrolytes, lambda increases slowly with dilution and can be represented by the equation. It can be seen that if we plot lambda m against C1 by 2, we obtain a straight line with intercept equal to the lambda naught m and slope equal to the minus a. The value of the constant A for a given solvent and temperature depends on the type of electrolyte, that is the charges on the cation and anion produced on the dissociation of the electrolyte in the solution. Thus, NaCl, CaCl2, MgSO4 are known as 1,1, 2,1 and 2,2 electrolytes respectively. All electrolytes of a particular type have the same value for A. Kohlrausch examined lambda naught values for a number of strong electrolytes and observed certain regularities. He noted that the difference in this of the electrolytes NaX and Kx for NEX is nearly constant. On the basis of the above observation, he enunciated that Kohlrausch law of independent migration of ions. The law states that limiting molar conductivity of an electrolyte can be represented as the sum of the individual contributions of the anion and cation of the electrolyte. Thus, if lambda naught A Na and lambda naught Cl negative are limiting molar conductivity of the sodium chloride ions respectively, then the limiting molar conductivity for sodium chloride is given by this equation, that is lambda m naught NaCl is equals to lambda naught Na plus lambda naught Cl negative. In general, if an electrolyte on dissociation gives new cations and new negative anions, then its limiting molar conductivity is given by this equation. Now here you can see the table 3.4. It is having the limiting molar conductivity for some ions in water at 298 K. H ion is having 349.6, sodium ion is having 50.1, potassium ion 73.5, calcium ion 119, magnesium ion Mg2 positive it is 106, OH ion 199.1, chloride ion 76.3, bromine ion that is 78.1, CH3COO negative that is the 40.9 and SO42 negative that is a 160. Now weak electrolytes. Weak electrolytes like acetic acid have lower degree of dissociation at higher concentration, and hence for such electrolytes the change in lambda m with dilution is due to increase in the degree of dissociation and consequently the number of ions in total volume of solution that contains 1 mole of electrolyte. In such cases, lambda n increases steeply on dilution, especially near lower concentrations. Therefore, lambda naught m cannot be obtained by extrapolation of lambda m to zero concentration. At infinite dilution, electrolyte dissociates completely, but at such low concentration, the conductivity of the solution is low that it cannot be measured accurately. Therefore, for weak electrolyte is obtained by the Corrosion law of independent migration of ions. At any concentration C, if alpha is the degree of dissociation, then it can be approximated to ratio of molar conductivity lambda m at the concentration C to limiting molar conductivity. Thus we are having value of alpha, but we know that the weak electrolyte like acetic acid, we are having this value. Now the applications of the Corrosion law, that is using Corrosion law of independent migration of ions, it is possible to calculate lambda naught m for any electrolyte from the lambda naught of individual ions. Moreover, for weak electrolytes like acetic acid, it is possible to determine the value of its dissociation constant once we know the lambda naught m and lambda m at a given concentration C. 3.5 Electrolytic cells and electrolysis. In an electrolytic cell, external source of voltage is used to bring about a chemical reaction. The electrochemical processes are of great importance in the laboratory and the chemical industry. One of the simplest electrolytic cell consists of two copper strips dipping in an aqueous solution of copper sulfate. If a DC voltage is applied to the electrodes, then CO2 positive ions discharge at the cathode, that is negatively charged, and the following reaction takes place, that is the CO2 positive plus 2 electron gives out Cu. Copper metal is deposited on the cathode and at the anode copper is converted into CO2 positive ions by the reaction, that is the copper gives out CO2 positive plus 2 electron. Thus, copper is dissolved or oxidized at anode and deposited or reduced at cathode. This is the basis for an industrial process in which impure copper is converted into the copper of high purity. Thus, impure copper is made an anode that dissolves on passing current and pure copper is deposited at the cathode. Many metals like sodium, magnesium, aluminium, etc. are produced on large scale by electrochemical reduction of their respective cations, where no suitable chemical reducing agents are available for this purpose. Sodium and magnesium metals are produced by the electrolysis of their fused chlorides, and aluminium is produced by electrolysis of aluminium oxide in the presence of cryolite. Now, quantitative aspects of electrolysis. Michael Faraday was the first scientist who described the quantitative aspect of electrolysis. Now, Faraday's laws also flow from what has been discussed earlier. Faraday's law of electrolysis. After this extensive investigation, the electrolysis of solution and melts of electrolytes, Faraday published his results during 1833 to 34 in the form of the following well-known Faraday's two laws of electrolysis. Number 1, first law. The amount of chemical reaction which occurs at any electrode during electrolysis by a current is proportional to the quantity of electricity passed through the electrolyte in bracket, that is solution or melt. Now second law, the amounts of different substance liberated by the same quantity of the electricity passing through the electrolytic solution are proportional to their chemical equivalent weights, that is atomic mass of metal divided by number of electrons required to reduce the cation. There were no constant current sources available during Faraday's time. The general practice was to put a coulometer, a standard electrolytic cell it is, for determining the quantity of electricity passed from the amount of metal, that is generally silver or copper, deposited or consumed. However, coulometers are now obsolete and we now have constant current sources available, and the quantity of electricity, that is Q, passed is given by Q is equals to IT, where I is the current. Q is in coulombs when I is in ampere and T is in seconds. The amount of electricity or charge required by oxidation or reduction depends on the stoichiometry of the electrode reactions. For example, in the reaction Ag positive plus electron gives out Ag. 1 mole of electron is required for the reduction of 1 mole of silver ions. We know that charge on 1 electron is equal to 1.6 into 10 to the power 19 coulomb. So therefore the charge on 1 mole of electron is equal to 96487 coulomb per mole. This quantity of electricity is called Faraday and is represented by the symbol F. For approximate calculation, we use 1F is approximately equal to the 96500 coulomb per mole. For the electrode reactions, Mg2 positive plus 2 electron gives out Mg and Al3 positive plus 3 electron gives out Al. It is obvious that 1 mole of Mg2 positive and Al3 positive require 2 mole of electrons, that is 2F, and 3 mole of electrons, that is 3F respectively. The charge passed through the electrolytic cell during electrolysis is equal to the product of current in amperes and time in seconds. In commercial production of metals, current as high as 50,000 ampere are used, that amounts to be 0.518 Faraday per second. Now 3.5.1, that is products of electrolysis. Products of electrolysis depend on the nature of material being electrolyzed and the type of electrodes being used. If the electrode is inert, that is platinum or gold, it does not participate in the chemical reaction and act only as source or sink for electrons. On the other hand, if the electrode is reactive, it participates in the electrode reaction and thus the products of electrolysis may be different for reactive and inert electrodes. The product of electrolysis depends on the different oxidizing and reducing species present in the electrolytic cell and their standard electrode potentials. Moreover, some of the electrochemical processes, although feasible, are so slow kinetically that all lower voltages these do not seem to take place and extra potential called overpotential has to be applied, which makes such processes more difficult to occur. For example, if we use molten NaCl, the products for electrolysis sodium metal and chloride or chlorine gas, here we have one cation NaIon which is reduced at the cathode and one anion, that is chloride ion, which is oxidized at the anode. During the electrolysis of aqueous sodium chloride solution, the products are NaOH, chlorine gas and hydrogen. In this case, besides sodium ion and chloride ions, we also have hydrogen ion and OH ions along with the solvent molecules H2O. So at the cathode there is competition between the following reduction reaction, that is sodium positive plus electron gives out sodium and H positive gives out electron. With the electron it is giving the half H2. The reaction with higher value of E negative is preferred and therefore the reaction at the cathode during electrolysis is preferred. So because the H ion plus electron gives out half H2, it is having the E negative Cl is equals to 0.00 volt and in the sodium reaction it is having minus 2.71. So higher one is preferable, but H ion is produced by the dissociation of H2O. H2O gives out H ion plus OH ion and therefore the net reaction at the cathode may be written as the sum of the above both reaction, that is H2O plus electron gives out half H2 plus OH ion. And at the anode the following oxidation reactions are possible. Chloride ion gives out half Cl2 plus electron, and the value of E negative is equals to 1.36 volt. And 2H2O gives out O2 plus 4H ion plus 4 electron, and the value of E negative is 1.23 volt. The reaction at anode with lower value of E negative is preferred, and therefore water should get oxidized in the presence of chloride ion. However, on account of overpotential of oxygen, reaction is preferred. Thus, the net reaction may be summarized as NaCl in presence of H2O gives out Na ion plus chloride ion. And the net reaction is NaCl plus H2O gives out sodium ion plus OH ion plus half H2 plus half Cl2. The standard electrode potential are replaced by electrode potentials given by Nernst equation to take into account the concentration effects. During the electrolysis of sulfuric acid, the following processes are possible at the anode, that is 2H2O gives out O2 plus 4H ion plus 4 electron, and the value for the E is equals to plus 1.23 volt. 2SO4 2 negative gives out S2O8 2 negative plus 2 electron, and the value for the E negative is 1.96 volt. For dilute sulfuric acid, reaction is preferred but at higher concentration of H2SO4, next reaction, that is 3.39, is preferred. 3.6 Batteries. Any battery, actually it may have one or more than one cell connected in series. Our cell that we use as a source of electrical energy is basically a galvanic cell where the chemical energy of the redox reaction is converted into electrical energy. However, for a battery to be of practical use, it should be reasonably light, compact, and its voltage should not vary appreciably during its use. There are mainly two types of batteries. 3.6.1 Primary batteries. In the primary batteries, the reaction occurs only once, and after use over a period of time, battery becomes dead and cannot be reused again. The most familiar example of this type is the dry cell, known as Leclanché cell after its discoverer, which is used commonly in our transistors and clocks. The cell consists of a zinc container that also acts as anode, and the cathode is a carbon graphite rod surrounded by powdered manganese dioxide and carbon. Figure 3.8. The space between the electrodes is filled by a moist paste of ammonium chloride, that is NH4Cl, and zinc chloride, that is ZnCl2. The electrode reactions are complex, but they can be written approximately as follows. ZnHg plus 2OH ion gives out ZnO plus H2O plus 2 electrons. At cathode, HgO plus H2O plus 2 electrons gives out Hg plus 2OH. The overall reaction is represented by Zn plus HgO gives out ZnO plus Hg. The cell potential is approximately 1.35 volt and remains constant during its life, as the overall reaction does not involve any ion in solution whose concentration can change during its lifetime. Here you can see in the diagram 3.9 commonly used mercury cell. The reducing agent is zinc and the oxidizing agent is mercury oxide. 3.6.2, that is secondary batteries. A secondary cell after use can be recharged by passing current through it in the opposite direction so that it can be used again. A good secondary cell can undergo a large number of discharging and charging cycles. The most important secondary cell is a lead storage battery. Figure 3.10, commonly used in automobiles and inverters. It consists of a lead anode and a grid of lead packed with the lead oxide, that is PbO2, as cathode. A 38% solution of sulfuric acid is used as an electrolyte. The cell reactions when the battery is in use are given below. At anode, it is Pb plus SO4 2 negative gives out PbSO4 plus 2 electron. At cathode, PbO2 plus SO4 2 negative plus 4H ion plus 2 electron gives out PbSO4 plus 2 H2O. That is, overall cell reaction consisting of cathode and anode reactions is Pb plus PbO2 plus 2 H2SO4 gives out 2 PbSO4 plus 2 H2O. On charging the battery, the reaction is reversed and PbSO4 on anode and cathode is converted into the Pb and PbO2 respectively. Here you can see the diagram 3.10, the lead storage battery. Another important secondary cell is the nickel cadmium cell, that is figure 3.11, which has longer life than the lead storage cell but more expensive to manufacture. We shall not go into details of working of the cell and the electrode reactions during charging and discharging. The overall reaction during discharge is Cd plus 2NiOH whole thrice gives out CdO plus 2NiOH whole twice plus H2O. Here you can see the 3.11 diagram, a rechargeable nickel cadmium cell in a jelly roll arrangement and separated by a layer soaked in moist sodium or potassium hydroxide. 3.7 Fuel cells. Production of electricity by thermal plants is not a very efficient method and is a major source of pollution. In such plants, the chemical energy, that is heat of combustion of fossil fuels of coal, gas or oil, is first used for converting water into high pressure steam. This is then used to run a turbine to produce electricity. We know that a galvanic cell directly converts chemical energy into electricity and is highly efficient. It is now possible to make such cells in which reactants are fed continuously to electrodes and products are removed continuously from the electrolyte compartment. Galvanic cells that are designed to convert the energy of combustion of fuels like hydrogen, methane, methanol, etc. directly into electrical energy are called fuel cells. One of the most successful fuel cells uses the reaction of hydrogen with oxygen to form water, that is figure 3.12. The cell was used for providing electrical power in the Apollo space program. The water vapors produced during the reaction were condensed and added to the drinking water supply for the astronauts. In the cell, hydrogen and oxygen are bubbled through porous carbon electrodes into concentrated aqueous sodium hydroxide solution. Catalysts like finely divided platinum or palladium metal are incorporated into the electrodes for increasing the rate of electrode reactions. The electrode reactions are given below. At cathode, it is O2 plus 2H2O plus 4 electron gives out 4 OH ion. At anode, it is 2H2 plus 4 OH ion gives out 4 H2O. Overall reaction being 2H2 plus O2 gives out 2H2O. The cell runs continuously as long as the reactants are supplied. Fuel cells produce electricity with an efficiency of about 70% compared to thermal plants whose efficiency is about 40%. There has been tremendous progress in the development of new electrode materials, better catalysts and electrolytes for increasing the efficiency of fuel cells. These have been used in automobiles on an experimental basis. Fuel cells are pollution free, and in view of their future importance, a variety of fuel cells have been fabricated and tried. 3.8 Corrosion. Corrosion slowly coats the surfaces of metallic objects with oxides or other salts of the metal. The rusting of iron, tarnishing of silver, development of green coating on copper and bronze are some of the examples of corrosion. It causes enormous damage to buildings, bridges, ships and to all objects made of metals, especially that of iron. We lost crores of rupees every year in account of corrosion. In corrosion, a metal is oxidized by loss of electrons to oxygen and formation of oxides. Corrosion of iron, commonly known as rusting, occurs in presence of water and air. The chemistry of corrosion is quite complex, but it may be considered essentially as an electrochemical phenomena. At a particular spot of an object made of iron, oxidation takes place and that spot behaves as anode, and we can write the reaction. Anode 2Fe gives out 2Fe2 positive plus 4 electron. Here the value of E is minus 0.44 volt. Electrons released at anodic spot move through the metal and go to another spot on the metal and reduce oxygen in the presence of H ion, which is believed to have available from H2CO3 formed due to dissolution of carbon dioxide from air into water. Hydrogen ion in water may also be available due to dissolution of other acidic oxides from the atmosphere. This spot behaves as cathode with the reaction. On cathode, the reaction is O2 plus 4H ion plus 4 electron gives out 2H2O, and the value of E is 1.23 volt. The overall reaction being 2Fe plus O2 plus 4H ion gives out 2Fe2 positive plus 2H2O, and the value of E is 1.67 volt. The ferrous ions are further oxidized by atmospheric oxygen to ferric ions, which come out as rust in the form of hydrated ferric oxide, that is Fe2O3 into XH2O, and with further production of hydrogen ions. Prevention of corrosion is of prime importance. It not only saves money but also helps in preventing accidents such as a bridge collapse or failure of a key component due to corrosion. One of the simplest methods of preventing corrosion is to prevent the surface of the metallic object to come in contact with the atmosphere. This can be done by covering the surface with paint or some chemicals, for example, bisphenol. Another simple method is to cover the surface by other metals, that is Sn, Zn, etc. that are inert or react to save the object. An electrochemical method is to provide a sacrificial electrode of another metal like magnesium, zinc, etc. which corrodes itself but saves the object. The hydrogen economy. At present, the main source of energy that is driving our economy is fossil fuels such as coal, oil and gas. As more people on the planet aspire to improve their standard of living, their energy requirement will increase. In fact, the per capita consumption of energy used is a measure of development. Of course, it is assumed that energy is used for productive purpose and not merely wasted. We are already aware that carbon dioxide produced by the combustion of fossil fuels is resulting in the greenhouse effect. This is leading to a rise in the temperature of the Earth's surface, causing polar ice to melt and ocean levels to rise. This will flood low-lying areas along the coast, and some island nations such as Maldives face total submergence. In order to avoid such a catastrophe, we need to limit our use of carbonaceous fuel. Hydrogen provides an ideal alternative as its combustion results in water only. Hydrogen production must come from splitting water using solar energy. Therefore, hydrogen can be used as a renewable and non-polluting source of energy. This is the vision of the hydrogen economy. Both the production of hydrogen by electrolysis of water and hydrogen combustion in a fuel cell will be important in the future, and both these technologies are based on electrochemical principle. Summary: an electrochemical cell consists of two metallic electrodes dipping in electrolytic solution. Thus, an important component of the electrochemical cell is the ionic conductor or electrolyte. Electrochemical cells are of two types. In galvanic cell, the chemical energy of a spontaneous redox reaction is converted into electrical work, whereas in an electrolytic cell, electrical energy is used to carry out a non-spontaneous redox reaction. The standard electrode potential for any electrode dipping in an appropriate solution is defined with respect to standard electrode potential of hydrogen electrode taken as 0. The standard potential of the cell can be obtained by taking the difference of the standard potentials of cathode and anode. The standard potential of the cells are related to the standard Gibbs energy and equilibrium constant of the reaction taking place in the cell. Concentration dependence of the potentials of the electrodes and the cells are given by Nernst equation. The conductivity of an electrolyte solution depends on the concentration of the electrolyte. Nature of solvent and temperature. Molar conductivity is defined by K upon C, where C is the concentration. Conductivity decreases, but molar conductivity increases with decrease in concentration. In increase slowly with decrease in concentration for strong electrolytes, while the increase is very steep for weak electrolytes in very dilute solution. Kohlrausch found that molar conductivity at infinite dilution for an electrolyte is the sum of the contribution of the molar conductivity of the ions in which it dissociates. It is known as law of independent migration of ions and has many applications. Ions conduct electricity through the solution, but oxidation and reduction of the ions take place at the electrodes in an electrochemical cell. Batteries and fuel cells are very useful forms of galvanic cell. Corrosion of metals is essentially an electrochemical phenomena. Electrochemical principles are relevant to the hydrogen economy. Thank you so much.